This is Anna DeMello, Jackie Gomez, and Ricky Shimizu working with Dr. Leslie Collins, Dr. Evelyn Stemp, and Dr. Boyla Mensah on our project, Novel Machine Learning Techniques for Brain-Computer Interface, or BCI, applications within the Data Plus program. Individuals with neuromuscular disorders are unable to communicate and move. BCIs can then provide a means of communication for these individuals. With the P300 speller, users focus on a character shown on the BCI interface, such as the one in the bottom left corner. The rows and columns are then flashed sequentially such that when the target character is flashed, a P300 ERP, or event-related potential, is elicited in the electroencephalography or EEG response. The BCI then analyzes the EEG data, such as that in the bottom right corner, to determine the user's intended character. However, data variability presents a challenge in transitioning BCI from the research lab to people's homes. This is because in training a classifier on a user's data, within subject variability causes a performance drop over time in the accuracy when applied to incoming data from that same user. When pre-training a classifier with other users' data, between subject variability causes a performance drop due to domain shift. Our goal is then to mitigate the performance drop due to variability with advanced pre-processing methods and transfer learning.
Training a machine learning model requires a lot of data and time. Since they are not always available, we want to use other subject data. However, we have illustrated a problem with this method in the figure on the right. The performance for cross-subject testing when trained and tested on different subjects is about 50% lower than within-subject testing when trained and tested on the same subject. In the figure, diagonal entries are within-subject testing and others are cross-subject testing. We would like to improve performance for cross-subject testing accuracies. We implemented 3 different transfer learning and signal processing methods to address this issue. For KLD weighted averaging, we take a weighted average of the pre-trained models. For fine-tuning, we fine-tune the pre-trained model. For X-zone, we apply the spatial filter. X-zone spatial filter has successfully improved the performance, as seen the better average accuracy and smaller standard deviation, while other methods have performed worse than the control. We'll continue trying to improve the performance by combining the X-zone filter with transfer learning techniques in the future.
We created a GUI to facilitate the uploading of documents to train and test the CNN model with X-zone spatial filter, which we created pre-transfer learning. Using the train button, you can upload EDF files that will be used to train the model. After that, you can use the test button to upload the files that will be tested against the trained model. The character selection accuracy will then be displayed. Using the menu in the upper left corner, you can go to the average response screen. The average target and non-target responses of the same channel are shown in the same figure. As more signals are averaged together, the signal-to-noise ratio increases, making it easier to distinguish an event-related potential. The target response's peak value appears about 200 to 300 milliseconds after the flash occurs. The non-target response is a representation of the stimulus presentation rate. Using the largest ERP from a row and column, the row and column intersection is used to determine which character is selected.